Welcome to Calculus. Today we will investigate how to verify solutions for differential equations. We'll take a look at a total of 4 examples. Our first example is a middle of the road, verify the solution of this differential equation. So I've got 2 equations here in my example number 1. The first one's y equals c times e to the power of 5x. The second equation is y prime, or the first derivative of y, equals 5y. So just to begin, just to identify parts, I need to say which one of those is my potential solution, which one is the original differential equation. So I know it's a differential equation if it involves a derivative. So my differential equation is going to be this second one, y prime equals 5y, which means my first equation is my potential solution. Now, for me, what I need to do in order to verify that this solution, y equals c e to the power of 5x, is a solution of my differential equation, I want to take and find the derivative of my solution. I want to say, okay, if y is c e to the power of 5x, then I need to discover what's the value of y prime. So I'm just going to take this initial equation, let's take its derivative. So I'm going to write y prime equals, and then I need to take the derivative of c e to the power of 5x. So I see I got to use the chain rule. I'll leave that constant coefficient in place. And then the derivative of e to the power of 5x is going to be e to the power of 5x. But because I've got a composed function in the power, I need to take the derivative of that g of x. And that's going to give me derivative of 5x is 5. So overall, the derivative of y is going to be 5 times c e to the power of 5x. Now, the claim here is that y prime equals 5 times y. That's what my differential equation is saying. And so what I need to make is essentially a substitution back in. I had the solution equation was giving me a definition for y. And that's saying that y equals c times e to the power of 5x. Well, I'm seeing that that piece of my derivative is still y. And so in fact, this derivative is going to equal 5y. And if I bring that initial part, that was finding y prime, that completes my proof or my verification that this solution is for that differential equation. Let's take a look at a second example. So our second example is looks like a circle equation. X squared plus y squared equals c, constant c, times y. So again, I can tell that that's my potential solution. The differential equation is the second one, y prime equals 2xy over x squared minus y squared. So again, I start off just by identifying what's my potential solution, what's my differential equation. So I want to find y prime. Now this example is a little different because it's not a function, it's a relation. I need to use implicit differentiation to find what's y prime. And I just got to keep in view another name that I could call y prime here is dy dx. So that's how I want to treat this example, is as so. I'm going to be looking for dy dx. So what I'm going to start off doing is I'm going to take the derivative of the solution equation. So that's going to give me 2x. And you got to keep in mind, I'm taking the derivative with respect to x. So when I get to this term y squared, definitely the derivative is 2y, but I need to record that it's the derivative of y with respect to x. And I can start to see that's where I'm going to find my expression for y prime. Well, let's keep going. So that equals the derivative of c times y, which is going to be just c again times dy dx. Now, if what I've identified as my y prime is dy dx, what I need to do in my equation currently is get those dy dx terms on the same side and set them equal to the expression. So what I'm going to do next is move some terms around. Let's do this. Let's take and subtract 2y dy dx from both sides. It'll cancel there on the left, and it's going to show up here on the right side. So what we've got next is going to be 2x equals c times dy dx minus 2y dy dx. And then so that I can solve for dy dx, I want to factor it out of that difference on the right side. See that I've got dy dx in both terms. So my next step, I'm going to pull dy dx to the left, and that's going to leave c minus 2y in parentheses, and that's going to equal 2x. So now to get dy dx solved, I just need to divide by c minus 2y. That'll cancel there on the right side. And this is my expression for dy dx. And let's lift it up. Let's lift it up. So currently this is what we got. And I'm going to flip that equation around. So dy dx, which again is another name for y prime. That's kind of my rationale here, is going to equal 2x divided by c minus 2y. Now I'm comparing what I've got at this point with the right side of the differential equation I'm trying to verify the solution for. So I can see that there's some parts there that are looking very, very much in place. But what I need to do at this point is I need to make some substitutions back in here for C particularly. I see that I don't have a C value in the differential equation on the right side. So to catch like what is C, I'm going to go back to the original solution where I've got C as a term, and all I need to do is just solve for C on that original is divide by Y. And so my expression that I'm going to plug in for C is this left side, x squared plus y squared divided by y. So let's make that substitution. So dy dx is going to equal 2x over, make my substitution in there for C. C is x squared plus y squared divided by y. And then pick up with my term minus 2y. So at that point, what I need to do is simplify the complex fraction. So to be able to do so in the denominator, I need both of these terms over y. So I'm going to put y below and above. So what I got in my simplification now is 2x over, now I can put it all in one numerator since I've got common denominator of y. So it's x squared plus y squared minus 2y squared. And I got some like terms there. Y squared minus 2y squared is going to be negative y squared. So my next step, it's going to be 2x over x squared minus y squared divided by y. And then to finalize here, I want to multiply by a y to cancel that denominator in the denominator. And we'll do so above as well. And I'm just going to carry down, this is dy dx still, dy dx. And with that cancellation, we have reached our final form in my numerator 2xy over x squared minus y squared. And that completes my proof. Again, where we start is the solution equation. And our goal is to reach the differential equation from the solution. Our third example is a little different. In our first two examples, we just wanted to verify that a certain solution was valid for a given differential equation. With this question number 9, we want to determine whether it is or not. We don't know whether y equals x squared is a solution for the differential equation that's given here. Let me go ahead and highlight xy prime minus 2y equals x cubed e to the power of x. So it's a little different in this term. What I need to do is note where I need to make some substitutions. So on this differential equation, since it's a little different, it's not just y prime, I need to plug in an expression for y. So I see that that's x squared from my solution here, 9. And I also need to plug in the derivative of y. So I do need to do that first here on the left. So y prime is going to be just 2x. And that's what I want to substitute. So for this question, what I'm trying to see is this actually true? Is y equals x squared a solution for that differential equation? So I'm going to start with that left side. X times, I'll substitute in for y prime 2x. Then I'm going to pick up with the differential equation, the left side again, minus 2, and then again times y. Y itself was x squared. So I just want to then simplify that and see, does that simplify to x cubed e to the power of x, the right side of the differential equation? So on the left here, we're going to have x times 2x is 2x squared minus 2x squared. And that cancels out that 0. And then I just want to compare it. I'm going to put a question mark over the equal side. Does 0 equal x cubed e to the power of x? It does not. And so what we would say is y equals x squared is not a solution of our differential equation x y prime minus 2y equals x cubed e to the power of x. Our last example involves a general solution and then asks us to take it a little further and find that the particular solution that satisfies the initial condition. So we start as we have done with our first 3 examples. I see that I've got a proposed solution, y equals c e to the power of negative 6x. I have my differential equation there is y prime plus 6y equals 0. So I just want to verify, first of all, is that a valid solution to the differential equation? So again, on the left side, I see that I need to make 2 substitutions. So y, which I've got already, that's c e to the power of negative 6x. I need to find also y prime. So to make those substitutions, let's find y prime first. So I'm just going to take the proposed solution, take its derivative. So that's going to be c times e to the power of negative 6x. But then I got to take the derivative of the composed function negative 6x. And its derivative is going to be negative 6. So we do have to use chain rule there. So simplifying, y prime is going to be negative 6c e to the power of negative 6x. So we're ready to make our substitutions into this differential equation. So I just found what y prime was. So negative 6c e to the power of negative 6x. And I'll pick up with the differential equation left side, so plus 6, and then times y, which again is c e to the power of negative 6x. Then I want to simplify. Does that equal 0? And pretty immediately here, I can see that it does. When I make the multiplication with that green 6, it's going to be negative 6c e to the power of negative 6x plus the same term, 6c to the power of negative 6x. Because that's a zero pair, definitely it adds to 0. And we have verified it. It is a valid solution to the differential equation. So that's all the same as what we've been doing. The new part is now to find a particular solution that satisfies the initial condition. So what that essentially amounts to is I want to use the point here, y equals 3 when x equals 0, as a way to come up with what's the value for c. The general solution can involve a constant that's given just as a variable. That's kind of a weird thing to think. But we keep it as a variable because it's a family of solutions. When I'm finding a particular solution, I'm actually finding a value for c and fixing it at a number. So the way we do that is we pick up our values for x and y. And essentially, I just want to take my solution equation and I want to plug in those values. So from my data here, y equals 3 when x equals 0. So I'm going to just write those over here. In fact, I'll go ahead and just put it x equals 0, y equals 3. And I'm going to pick up my solution equation, which is y equals c e to the power of negative 6x. And then I want to make a substitution. So for y, I'm going to plug in 3. Pick up with the solution equation equals c e to the power of negative 6 times my x value there is 0. And I just want to solve for c. So I can see here definitely I'm helped out. E to the power of negative 6 times 0 is e to the power of 0, which is 1. That cancels out. Immediately I see c equals 3. And so my particular solution is going to be, I'll write it out here. It's the particular solution is going to, so again, I'm picking up the original solution, y equals, but instead of c, I'm going to plug in 3 e to the power of negative 6x, and that is complete. Thank you for joining for this investigation of verifying solutions for differential equations, and then in this last example, finding a particular solution to satisfy the initial conditions. See you soon.